Hey guys, and welcome to another 5-Minute Frenzy with Ryan Gapinski. Today we'll be concluding our Intro to Invasive Ventilation series. We're going to be focusing on the use of ABGs to optimize mechanical ventilation. Now, depending on the model of ventilator that you're using, you will see a screen that looks pretty similar to this, or at least you should be able to find these parameters somewhere on it. The settings we're going to be focusing on today are frequency or rate, tidal volume, oxygen percentage or FiO2, and PEEP. I'll go into the other parameters in a future session. For the purposes of this presentation, there are really only two reasons to make a change to ventilator parameters in the emergent setting. Either the patient is not oxygenating or the patient is not ventilating. And there are specific settings that deal with each of those conditions. First, we'll talk about oxygenation. If your patient is hypoxemic, as evidenced by either a decreased pulse oximetry or a PaO2 of less than 80 on an ABG, the two parameters that can be manipulated to correct the issue are FiO2 and PEEP. Henry's law states that as we increase the concentration of a gas above a liquid, the amount of that gas that is dissolved in the liquid increases. Simply put, that means that if I want to increase the amount of oxygen in the blood, I need to put more oxygen in the lungs. In the emergent setting, we typically start patients off at 100% or an FiO2 of 1.0, and then we wean them from there, if and when appropriate. If you have a patient who's hypoxemic and they are not at 100% oxygen, this should typically be the first change that you make. The second parameter you can change to mitigate hypoxemia is to add additional positive end expiratory pressure. It makes sense that if we're able to recruit additional alveoli, and even more so that if we're able to prevent atelectasis, that we will be able to increase oxygenation. If there are more oxygen-filled alveoli coming into contact with the pulmonary capillary beds, then it stands to reason that there will be more room for gas exchange. Remember, though, as I've mentioned before, PEEP is not entirely benign, as it can lead to decreased systemic return as well as possible barotrauma. The second situation we will look at is hypo or hypercapnia. This value can also be assessed both invasive and non-invasively through either a quantitative end-tidal CO2 detection device or the PaCO2 value on an arterial blood gas. Derangements involving carbon dioxide are mitigated by adjusting minute volume, and much like before, this can be done in one of two ways. Remember that minute volume is the product of respiratory rate and tidal volume. The first parameter that affects minute volume is the frequency or rate of respiration. In an adult patient, this tends to provide the most change with the littlest effort. For example, if I have a patient with vent settings of rate of 12, tidal volume of 500, and I change the rate to 14, I have increased the minute volume by 1 liter. I would have had to increase the tidal volume by more than 80 milliliters to affect the same change. As we've already mentioned, tidal volume is the other parameter that can be manipulated to account for minute volume. Tidal volume should be set based on ideal body weight, not actual body weight, and should typically range between 4 and 8 milliliters per kilogram. We need to be careful when adjusting tidal volume, especially when increasing it, as this can lead to ventilator-associated lung injuries and barotrauma. Keep in mind that these are not either-or settings, and sometimes, in order to dial in the best minute volume for the patient, you will have to make changes to both of these parameters simultaneously. An easy formula to get you into the ballpark of where you need to be as far as minute volume is concerned is to take your current PaCO2, multiply that by your current minute volume, and divide that answer by your desired PaCO2, which is typically 40. That will provide you an approximate minute volume to shoot for. For example, let's take a patient who is being ventilated at 10 times a minute with a tidal volume of 350. That gives us a minute volume of 3.5 liters. After being on the ventilator for 15 to 20 minutes, an arterial blood gas is drawn, and the PaCO2 value is returned as 52. Our desired PaCO2 for this patient is 40 millimeters of mercury. If we plug the numbers into the formula, we get this. 52 times 3.5 is 182. Divided by 40, that equals 4.55, indicating that we need to increase our minute volume by just over 1 liter. Changes for this patient might look something like this. Increase the rate from 10 to 12, and increase the tidal volume from 350 to 375. This will give us a new minute volume of 4.5 liters. I have a little bit of time left, so I wanted to touch on pressure support really quick. For a patient that's on SIMV or IMV, the clinician can opt to set the ventilator to provide pressure support for all of the patient-initiated breaths. In the case of a patient where pressure support is set to 0, the ventilator will not provide any respiratory support for a patient-initiated breath unless it triggers a full breath from the ventilator. If the pressure support was set to, say, 5 or 10, and the patient-initiated breath was not close enough to trigger a regularly scheduled breath, the patient would still receive a small amount of air from the ventilator. Guys, that's all I have for you today. That completes the Introduction to Mechanical Ventilation series. Be on the lookout for an intermediate series coming soon. Thank you for joining me today, and feel free to drop me a line on Twitter at RyanGapinski2, and I'll talk to y'all again real soon.